Good afternoon, everyone. I'm Maitreya,
And I'm Ishaq.
and we'll be presenting the Sierpinski-Mazurkiewicz Paradox.
So let's get started with the formulation. The year 1914, the mathematician Sierpinski proposed a very interesting question. Can there be a subset of the 2D plane such that I can partition it into two disjoint subsets, A and B, such that A is congruent to B and the two are congruent to S? By congruence, I really mean this. Any two sets X and Y are said to be congruent if there exists a special function called an isometry, which maps one to the other. An isometry is basically any function which preserves a notion of distance between the input points and the output points. So there is a theorem which allows us to characterize every such isometry into a linear transformation followed by a translation component.
I think this is the.
So that was an isometry, I explained, right? In the intuitive setup of geometry, yes. So these two triangles are related by an isometry because I can apply a linear transformation on this, which will basically just be rotating these points about an origin and then translating the whole thing over here, assuming that these are the same dimensions because we want to preserve the distance. Also, emphasis on the fact that after applying an isometry, we want it to equal the set in R2 plane, which means they are the exact same set of points. So two figures which are separated by a distance, even if they match in orientation, they are not said to be the exact same set.
So now we have an example that does not satisfy the conditions of our problem. Let's say S is everything to the right of the y-axis. It is decomposed into A and B. A is everything to the right of the line x equal to 1, and B is everything in between them, as the diagram suggests. So there's an isometry that maps A to all of S. That is simply translating A to the left by 1 unit, but it does not satisfy the conditions of a problem because we don't have any isometry that maps B to all of S. Another example that does not work. We're translating and rotating A and B in some order, but they're going outside S. Not only do we want both of them to be inside S, we want both of them to equal S.
Now, why is our problem paradoxical in the first place? We are asking there to be a set, let's call it an orange for now. So I want an orange such that I can break the orange in any arbitrary fashion, or let's say any particular fashion, such that each of those two pieces, upon movement and rotation, will give me back the orange at the same location. So I have produced two copies of the orange at the same location from two proper subsets. I mean, this seems counterintuitive in so many levels. There is a more rigorous formulation of such sets. In the Journal of Geometry, in the year 1990, they defined a paradoxical set to be any subset of a metric space which can be decomposed via a partition, such that each set belonging to the partition can yield back the original set upon performing isometries.
Now, does such a subset S of the real plane exist? Turns out it exists. It was found by Sierpinski student Mazurkiewicz, and we'll be constructing the set S. We construct a set of complex numbers. Every complex number is of the form A plus IB, and to that there is a corresponding point in the real plane, A comma B. So here's set S. Take any polynomial with non-negative integer coefficients. We have an example. Evaluate that polynomial at e to the I. You'll get a complex number. We have that complex number. Put that complex number into S. Do this for all such polynomials with non-negative integer coefficients, and you'll get set S. S is decomposed into A and B. We have A, again, polynomials with non-negative integer coefficients, and the constant term is not equal to 0. The previous example works again. constant term is 5, not equal to 0. Evaluate all these polynomials at e to the I, you'll get complex numbers. These complex numbers form the set A. Set B, again, polynomials with non-negative integer coefficients, and the constant term is 0. We have an example, 7x squared plus x. Evaluate these polynomials at e to the I, you'll get complex numbers. These complex numbers form set B. A and B are disjoint. This is because e to the I is transcendental. We take this fact for granted in this presentation. This means that e to the I is not the root of any polynomial with integer coefficients. Suppose some element of A equals some element of B, and these are all polynomials with non-negative integer coefficients. Then e to the I is the root of the polynomial P minus Q, and this contradicts the transcendental nature of e to the I. Hence, A and B are disjoint sets.
Now we will proceed with defining isometries which will map A and B back to S. For A, simply consider shifting it to the left by 1 unit. That is a valid isometry, and in the complex plane we can characterize it by subtracting 1.
Can you define P again? Go back to the.
Oh yeah.
You didn't specify it's just a polynomial.
E is a polynomial with non-negative integer coefficients. And A and B.
We're evaluating that at e to the I, we'll get a complex number. That complex number
It's any degree.
It can be any such polynomial. And we have an example here, 2 into e to the I plus 1. It's an element of A since the constant term is non-zero. We can subtract 1 and we get 2 into e to the I, which belongs to S. For the set B, our isometry will be rotation clockwise by 1 radian about the origin. That can be characterized by multiplying e to the minus I to the relevant element. We have another example which maps an element from B to S. Now, the surjective nature of these isometries can be proven by taking a general polynomial applied to e to the I, call it x. Now, upon adding 1, I obtain the following polynomial. With a constant term of a0 plus 1. Now, since a0 is non-negative, a0 plus 1 is clearly positive. Yes. A0 plus 1 is clearly positive. Hence, it does belong to the set A. We have created a pre-image in A. Now, multiplying by e to the I will yield a pre-image in B. Clearly, the constant term is killed upon multiplying e to the I, hence it belongs to B, and we have a valid map between A to S and B to S.
You also need an isometric property. So distances.
Yes.
Yes. Since these are translation and rotation, geometrically speaking, they do preserve the standard Euclidean distance which we consider in our.
This is translation to the left by 1 unit, subtraction by 1. This is just rotation.
So yes, I have given you an orange which can be broken into 2 parts. Moving 1 to the left and rotating 1 radian will give you back the same orange.
But the catch is orange is unbounded.
Yes, the catch is the orange isn't really a nice orange because first of all, such a set can't even be rendered by a computer. Like set of all polynomials applied to a number. You can't even visualize it, and moreover, it's unbounded. The coefficients can be arbitrarily bound. Can we do it for a bounded set? It turns out you cannot with the limited notions we have employed, simple algebra and isometries. Upon invoking a stronger theory, namely the axiom of choice, we can indeed produce a bounded set which has a paradoxical property as defined. It turns out a decade later, two mathematicians, Banach and Tarski, provided an argument for a bounded set being paradoxical in the same journal which Sierpinski and Mazurkiewicz had founded in that period. Any questions?
Can you tell us about the Banach-Tarski paradox?
That's up next.
That's a fact.
Thank you. Hope you enjoyed
Hope
it.
you enjoy.